Let's do a quick gut check. We're going to look at abstract categories and concrete categories and try to see what's the difference in approach and how we should view them differently. So first, how do we think categorically? A priori, all categories are abstract, meaning that we should initially approach any problem in terms of objects and arrows in mathematics. We know that set theory is very descriptive and can encode all of our mathematical objects, but are all mathematical objects a priori sets? This is obviously not the case. We do not need set theory to do mathematics. Instead, we should think of set as being able to model mathematical theories. It's an encoding. Since a theory is then understood by its models, we see that set theory is important, and so we should try to understand set theory. We will see that we can lift properties from the category of sets to other categories which behave similarly to sets, the so-called elementary toposes. Then we could do mathematics with this topos as our encoding environment. And so it's the category theorist viewpoint that every property should be reduced to the concept of an arrow and not to element. So it's a change in perspective. You have to get your brains to stop thinking in terms of trying to look inside objects and to the elements and try to kind of step back and see everything as arrows. Let's just give you a few questions where you can maybe think about this. So A, how can we describe an element relation X in A as an arrow in the category of sets? So you want to say that an element is a certain type of arrow. B, what do you think is the most fundamental concept in mathematics? Do you think it's function, element, set? Maybe think about this and try to explain why you think that. C, explain why the free group, which we're going to denote by fx, so we have a set x and we're taking the free group on it, is not an abstract categorical property, i.e. there is no property of objects and arrows in group which will let us know whether or not a group is free. We need something else. D, explain how a regular projective object in the abstract category, in an abstract category, is a reasonable substitute for the concept of a free object. Next, we want to look at the definition of concrete categories again. So why are concrete categories defined as faithful functors? We discussed the data structure properties approach to defining a concrete category. Of course, there are many concrete categories which do not fit into this scheme. Why do we generalize to such an extent? Why do we not define a concrete category as one that has this data structure properties presentation? For one, there are often many different data structure properties which describe the same abstract category. So a concrete category is a presentation-free approach, or it's a presentation-free definition. More conceptually, you may want to view every functor you see f a to b as a model of A objects and arrows, A objects and A arrows in B. Then a concrete category is one which faithfully models A arrows as B arrows. Why not the objects as well? Well, the short answer is that a category and functor is determined completely by the arrows. We can forget objects by taking the identity arrows as proxies, and so you can actually define a category just in terms of the arrows. Finally, we want to look at a common mistake that, when people say concrete categories, sometimes they think certain categories they think they're structured sets, they actually aren't, at least in this framework. So don't make this mistake. Since all of mathematics can be encoded by sets, it is tempting to think that all categories are concretizable over a set, i.e. there exists a faithful functor to set from any category. It is true that all small categories via the Cayley functor are concretizable over set, but this is not the case for large categories, which are most of the categories that we're interested in. We will not go into detail since the proof of this is non-trivial, but one such category which is not concretizable over set is the category of homotopical topological spaces. It is tempting to think that the objects in this categories are sets equipped with a topology and the arrows are continuous set maps, which preserve some structure up to homotopy. But this up to homotopy is a property of the arrows, not the objects. So this is not a data structure properties presentation as we discussed in the previous sections. And in fact, there is no faithful functor from the category of homotopical topological spaces to set. Whenever we take equivalence classes of arrows like we have for this homotopical topological space category, and we construct a new category, it's often the case that when we had a concrete category, for example, the category of topological spaces over set, we lose this property when we take the equivalence classes of arrows. So we have a few more questions we want you to think about. A, give 3 different data structure properties presentations for the concrete category of topological spaces over set and show that they have the same fibers over an arbitrary set. And we're going to show that there's many different data structure properties presentations and they're all somehow the same. They're concretely equivalent, isomorphic to one another. B, show that the power set functor, which takes the opposite category of sets to set, is faithful, so that set op is concretizable over set. C, what is the easiest way to show that every non-empty thin category is concretizable over its dual? And a hint we give is that you should think of the simplest kinds of functors and then show that there is a factorization. D, are there categories A which are not concretizable over its dual, AOP? So B, we showed that set actually does have a faithful functor from its opposite category to itself. But are there categories where there is no faithful functor from AOP to A or A to AOP? These are, you just take the dual functor and that'll give you the other. E, do you feel comfortable saying that 2 mathematical objects are the same when they are simply isomorphic? What about equivalent categories? Can we say that equivalent categories are somehow the same? If equivalent categories are the same, how should we view the concept of amnestic and transportable, which are not abstract categorical properties, i.e., they're not invariant under equivalence? In a subsequent section, we will see that all concrete categories are concretely equivalent to a uniquely transportable refinement of it. So if you believe that we can relax the notion of sameness to just equivalence, we may as well just take all concrete categories as uniquely transportable, since that is the most desirable property of a concrete category. However, in my opinion, it is useful to understand the distinction between various concrete categories because there is an ontological difference. For example, I consider metric spaces and continuous maps in the non-uniquely transportable category of metric spaces as inherently different than metrizable spaces in the uniquely transportable refinement top M. As a final thought, mathematics is not just about solving problems, but also about formulating them in a proper context. Category theory finds the commonalities of mathematics in order to simplify and organize our understanding. If we fix a category X and consider concrete categories E over it, we can put on our X goggles to understand E. So the best kinds of concrete categories are those with a relatively well-understood base category and a more complicated concrete category E over it.